Hey everybody, this is Professor Corey and Professor Victoria. We are the Professors Du Bois, and today we wanted to just give an additional video solution to a problem in your Mindtap, and this is in Chapter 11. Specifically, this is 11.2a, and this is a really, I think this is a very confusing question. It takes a minute to wrap your mind around it, but it's really a great application of using the ideal gas law and using vapor pressure. So we just thought we'd try to walk through this and talk about some of the things that make this difficult and how to get around that.
Yeah, you can do it. It's just a little confusing historically for students, so we just wanted to walk you through it.
Okay, so we have a dorm room here with dimensions on the dorm room. They're in meters, and we drew this little cube box to represent this space. So essentially what we're saying is it's, 3.82 meters. That's one of the dimensions, and we've got a 4.88, and the last dimension is 3.30. Now, these are all in meters, and we can calculate a volume using length times width times height, something you probably haven't done in a long time, but we can multiply those three. But what happens is when we multiply meters times meters times meters, we end up with a unit of cubic meters. So the volume of this room is going to be 4.88 times 3.82 times 3.30. Those are all meters. So we end up with 61.52, and these units are meters cubed. So you see that each of these is meters, and I left the units out. I shouldn't have. Each of these is meters. Meters times meters times meters is meters cubed. Now, that's not a typical volume that we use, and when we use the ideal gas law, we're really driven by the gas law constant, R, which has units of liters, atmospheres, mole, and Kelvin. So I need to get this to liters. Now we put this in for you up here. We put the conversion factor in.
That's not on Mindtap.
No.
It's not in the question.
So we gave that to you. And if you remember, we can convert by using dimensional analysis. So I'm going to take this number and put it over 1, or you know what, I'm just going to put it over a stick figure. And I know I need my cubic meters in the denominator, right? So they'll cancel. And what goes with cubic meters is the 1, and the other part of that factor is the 1,000 liters. So my cubic meters cancel, and I've got units of liters. I have to multiply by 1,000, and that's essentially moving the decimal place to the right 3 places. So I could say 61,520. I'll put a decimal in there, liters. So this is the volume of the room.
So what are we doing? I mean, let's kind of back up and kind of talk about what we're doing and why we want even the volume.
That's a great point.
Yeah, so the question is saying we want the student wants their plants to be hydrated, right? So they're going to leave some water in the room, and we want to know if all of the water that they're leaving will evaporate completely. So we've made some assumptions. The room is airtight. There's no water to begin with. So we really need to think about this concept of vapor pressure. And the vapor pressure of water, it's given there as 23.8 millimeters of mercury at 25 C. So at 25 C, that means that we can evaporate water up to the point that it exerts a pressure of 23.8. Then it's saturated. That's the most water it can hold. Even if you have more water there available, it cannot evaporate. Or if it evaporates, it will also condense. So we have a maximum amount. So the question is really asking the amount of water that we're putting in the room, which is this 1.94 liters, will it all evaporate? So will it reach that saturation point? So we want to figure out what the pressure would be if it all evaporated, and then compare that to the vapor pressure. And if it's higher, then it can't reach that. The maximum amount is the 23.8, and it'll just leave some as a liquid. And if it's lower than that pressure, if the pressure of all of that water evaporating is lower then it will all evaporate and we don't actually reach the vapor pressure.
Yeah, so this is it's a pretty common application of the gas law. We're solving for the pressure, and that's something that's really, really important is when we solve for the pressure, we may get a value that's greater than 23.8, but this is just theoretically. This is like, in theory, if it were all to evaporate, this would be the pressure. Vapor pressure is the reality. I like the word saturated, like you said. This is as much pressure that can happen at this temperature. So we're gonna solve for pressure using the ideal gas law. And there's another thing that's kind of confusing in here is they gave us a volume here, this 1.94 liters, and that could throw you off because typically we can use our units and say, oh, that's a volume unit. Let's put that in for V. Not in this case. We needed the volume of the room, which we calculated. So what do I do with that? I mean, 1.94 liters of water. Wait, where do I go with that?
Well, let's write down our PV equals nRT.
I'm going to write that over here and
think about that.
Probably regret that later. Now I know I've got the volume of the room, and I'm going to write that over here too. 61520, and that's liters. Let's see, I know R, that's the ideal gas law constant. I might as well, get the low-hanging fruit here. The temperature they gave us, it was 25 C, and notice on the R value we have units of Kelvin, so I might as well just put that into Kelvin, and I do that by adding 273.15 to the Celsius temperature. So that's 298.15 Kelvin.
And we're solving for pressure.
We're solving for pressure, so we need an N. We need the number of moles.
And since we're talking about the pressure of water, we need the moles of water. Remember, we were saying if we assume that all of the water evaporates, what pressure will it have? So that is the moles of the water that we put in the room. So that's where what we're going to use that 1.94 liters. We have to convert that to moles and put that as N in our PV equals nRT.
All right, so what we need to use here is the density of water to get our liters into a mass, which we can then use the molar mass to get the number of moles.
And you should know that 1 milliliter is, well, we don't have to go to cubic centimeters, do we? We can just say we know that 1 gram is 1 milliliter of water. So we're going to convert this to milliliters first, and then convert it to grams. So 1 milliliter is 1 gram of water, and that's at a constant temperature, standard temperature. But you should know that. You should know that conversion for density of water. So now we can go to grams, but we can do one more step.
Oh yeah?
Yeah. We could just do one more step.
Let's put the grams
and change it
to moles. So 1 mole of water, I'm going to just put water here to make that clear. That's 18.016.
And we get that from the periodic table.
So that's 2 hydrogens, 1 oxygen. And when you get a lot of experience, you start memorizing these for some reason.
Grams per mole. So our moles come out to 107.7.
Now, in this question, all of our data, actually our temperature at 25 degrees C is just 2 sig figs. All the rest of the data is at 3 sig figs. So I was going a little above, and I figured I'd round at the very end of this problem.
Well, let's make our temperature to when we add 273.15, we have to round to the even number of decimal places.
That's a good point.
Like no decimal places. So
yeah.
It would be 298.
That would just be 298.
And that is 3 sig figs.
It is. Good. And we'll round to 3 at the end. So I think we might have everything we need here, right? I'm going to say P.
P is what we want.
Times the volume of the room. So that's times 61520 liters equals N. This is the number of moles. This is the water. 107.7 mole. And N now times R. 0.08 0.2057. This is liters times atmospheres over mole times Kelvin, nRT, and I've got my 298 Kelvin. So my Kelvin's going to cancel here, my mole's going to cancel. And the way I like to do it, I like to just multiply the three numbers, but I could do this all in one step. I could multiply 107.7 times the 0.082057 times the 298, and then divide by the 61520. Or what I usually do is I'll leave this, I'll do it in two steps, but there's many ways to do the math. So this would equal 2.635 times 10 to the third. Oops, 3 doesn't look very good. And what I'm left with for units is liters times atmospheres. So now I'm going to divide by liters. 61520. Whatever I do to one side, I have to do to the other. These liters are going to cancel, and I get a pressure in atmospheres.
Yay. That's what we wanted.
Which is 0.0428 atmospheres. However, they gave us the vapor pressure in millimeters of mercury. So, well, actually, the question says calculate the pressure of the water vapor in millimeters of mercury. So again, I'm going to, over my stick figure.
This is another conversion that you really should commit to memory, is 1 atmosphere is 760 millimeters of mercury.
So my atmospheres cancel. I put the atmosphere in the denominator over here, and that's why I like to make this a fraction. That's why I'm using the stick figure. So I'm just going to multiply, and I'm going to have units of millimeters mercury, and this is going to be 32.55. I'm going to go to 3 sig figs now. So 32.6 millimeters of mercury, and this is just a theoretical.
If it all evaporated, that's the pressure that the water would be exhibiting within that space. That doesn't mean that it can reach that. Now we have to compare to our vapor pressure. So the saturation point, the point at which it can hold no more, is 23.8. So once the water evaporates and reaches that point, it's going to stop. So we'll never reach 32.6 millimeters. And in fact, we will have some water left over. So will it all evaporate? No, we'll have some left over. If your pressure that you calculated was less, then your answer would be yes. It can all evaporate, and it's still less than the vapor pressure.
Okay, so I'm just going to say that one more time. The pressure we calculated was a theoretical pressure if all of the water evaporated. However, because the vapor pressure at that temperature is 23.8, we can't go any higher than 23.8. And since we had a value that is greater than 23.8, what that means is the room is going to be at 23.8 millimeters of mercury, and there's going to be excess water which did not go into the vapor phase.
Hope this helped.
All right, thanks for watching. Stay tuned. More helpful instructional Chem 112 videos coming from the Professor's Du Bois.
Bye-bye.